Do we have a live stream I can retweet? Or do you have a live stream I can retweet before we start?
It's going to be up in 1 second on. Hang on, I retweeted. Once it's on.
Hey.
Retweet that shit, folks.
So it should be there.
All right, cool, where are we? Yep. Okay, so for those joining from the stream, or I suppose are watching it a day or two later, we're gonna try doing a live coding of an entire Lightning implementation from 0 to sending ourselves payments and opening channels with ourselves from 2 nodes based on code that we will write live from nothing. So we're going to use the Rust Lightning library, right? So the theory of Rust Lightning is you have a library that provides all of the Lightning implementation parts. All of the hard parts are done for you. This includes things like managing a list of channels, generating messages to send to your peers, receiving messages from your peers, doing all of the signatures and verifying what your peer does, and it knows how to punish your peer if they misbehave on chain, et cetera, but it doesn't do any of the parts where you might want to make your own decisions. So it doesn't implement an on-chain wallet. You have to bring your own on-chain wallet. It doesn't implement actually downloading and syncing the blockchain. You have to do that yourself somehow. It doesn't implement actually talking to things on the network. Again, you have to do that yourself somehow, although there's an optional additional thing that I'll be using today that implements that piece for you. And so the theory of this basically is maybe you're an existing wallet vendor, so you already have a wallet that you've built that you're using, and so all of those parts are you've already got those implemented, right? And you don't want to just take LND or take something that exists, and then you have to like download the chain twice because LND will download it, and your existing on-chain wallet obviously knows how to download the chain. So you don't want to like download the chain twice, have 2 on-chain wallets, because of course LND or C Lightning have built-in on-chain wallets. So if these are things that you already have, you can just use them, and it provides an easy way to integrate Lightning into an existing wallet. The other kind of target use case is if you want to run the full Lightning protocol stack on a hardware wallet. This is, in fact, why Rust Lightning doesn't send and receive messages on standard syscalls of actually making TCP connections, because in theory, you might want to run the Lightning implementation on a hardware wallet, and then, of course, to send a message to your peer, you're going to have to send that over the USB interface somehow or over some similar interface, and then the computer will actually send those messages to your peers. And so it's designed to be really flexible and hopefully do all the hard parts for you. And so I've actually got over here on the right side, I have a working demo that was hacked together maybe 6 months ago. And so if everything falls apart and nothing works, I will just be showing you that. But hopefully, we can get this working without resorting to that. So first, we're going to pull up the documentation for Rust Lightning. If you've never used Rust, there's great built-in documentation stuff in Rust. And so this is all automatically generated from source code anytime there's a new version. And yeah, so we're going to start with there's kind of a few pieces of Rust Lightning that you have to use. First of all, there's the channel manager, which does what you think. It manages a list of channels. It keeps track of state. It forwards payments from different channels. It generates messages that you're going to have to send to your peers. All of the good stuff that you might expect a Lightning node to do. It's kind of the core piece of the Lightning node. There's also channel monitor, which is kind of an abstraction that allows you to separate out the chain monitoring and on-chain punishment of any misbehaving peers from the rest of the channel logic. This is really nice because you might want to run several redundant copies of the channel monitor logic. Maybe you're going to run the channel monitor logic on the actual laptop and the channel manager and all of that kind of stuff on the hardware wallet. Maybe you're going to have a watchtower or several remote servers that are all doing the channel monitoring. And so by abstracting that out into separate pieces and having some little glue between them, you can trivially just run a standard Lightning node, or you can add some more complicated logic based on what you might want in your application. So maybe you're a wallet that runs on multiple devices, and users sync their wallet across multiple devices. There's all kinds of things you might want to play with, but by separating that out, we let you make that decision, the developer. Finally, of course, we have router, so doing all of the routing logic, and peer handler, and this is obviously the piece that sends messages to peers. So the first thing we're going to do, if I recall correctly, we're going to run, is that the right thing? I'm actually going to use fancy Rust async framework stuff. But what we're going to do is we're going to, of course, try to create one of these channel manager objects. So there's a number of things we need to pass to it, all of which we're going to need this. Use Lightning ln channel manager. So we need to tell it what network we're on, obviously. It's kind of important. And so the underlying...
Channel manager H.
Huh?
It's a manager point manager.
Ah.
In the use.
Man.
In the use. In the use.
Man. This is going to be really fun. So there's a number of, we're obviously going to do this on reg test because otherwise we're going to sit here waiting for blocks for a half an hour, which is not going to be fun. So, as you might expect, because this doesn't do any logic around the chain, you have to provide your own fee estimator, and there's these objects for like channel monitoring. So I'm going to cheat a tiny bit here, and I actually have a chain monitor class which does the fee estimation. All it really does here, you can see it is going to call an RPC client, so it calls estimate smart fee against Bitcoin Core node. So what we're going to do here is we're going to try to use a Bitcoin Core node as the underlying on-chain wallet. So we're just going to make RPC calls to it for fee estimation, syncing the current chain, and actually generating transactions when we want to fund a channel. So there's things about broadcasting transactions, and then there's a bunch of logic here to actually find fork, right? So if the blockchain does a reorg, we have to see that because we're polling. We have to walk back the chain and then sync back to where we were. And doing that in a polling manner, you have to actually like walk backwards with a bunch of RPC calls. It's a little easier, obviously, if you're syncing the chain. So yeah, we're going to build one of these. Fee estimator. Arc new estimator new. And then we're going to regularly update its values. RPC client. We need to build an RPC client. Was this on chain on there? So of course we also have a RPC client class, which you just provide basic things to, as you might expect. So username and password and host port. So we're going to do this RPC client new. Let's say we're going to make it user:pass, and of course 18332. Is that the right port for testnet or for reg test?
I think it's 2000.
18332?
I think the one needs to be 2.
28332. You'd think I'd know this by now. Cool, so that should just work. And then because just of the nuance of the way we're doing async IO here, everything goes in these arcs, which are atomic reference counted objects. That just means they're reference counted objects instead of being, they're allocated on the heap instead of on your stack, and they're atomically reference counted. Shared pointer, if you know C++, just a different term for shared pointer. And then what we're going to do is every few seconds, interval, timer, interval, new. Yeah, new duration. Every, let's say, 10 seconds, we're going to update our fee estimates. Implement stream. So we're using also a little bit of fanciness for there's these fancy new fangled async IO stuff in Rust called Tokyo, which will eventually become kind of part of core Rust, but for now it's this separate crate, which is actually super nice. And what's the API? On chain monitor. So we're going to call update values with our fee estimator. And yeah. Cool. So I'm sure this won't actually build, but we're going to try it anyway. Whoops. What did I do? New interval. Ah, right. Right. Okay. Anyway, I'm going to copy some of this because otherwise I'm just going to sit here forever. So where is that? That is way down here. All right, whatever. So some other things we need to do. So right, our channel manager creation. Where did I lose it? Channel manager creation. So it's reasonably good docs on Rest Lightning, but we have all these different things. So we have this, so we created our fee estimator that's going to update regularly. Now we need to create this mini channel monitor object, right? So this is a generic API that says, yes, our channel manager or somehow our channel got an update from the user, whether we sent a payment or we forwarded a payment or we received a message, whatever happened, we had an update. And so we need to do something useful, right? So normally what this means is you get called, you have this add update monitor call, and you have to persist it to disk, right? So normally anything that happens in Lightning, in order to be safe, if something happens in the channel that you're now going to need to make sure you monitor the chain for, you have to write that information to disk somehow, you have to call fsync, you have to make sure that it's on the disk, blah, 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 before you take any action on that basis. Otherwise, if your computer crashes or something at the wrong moment, obviously you can lose money. So that's not ideal. And so we provide this general interface where you have to implement monitor updating and do something useful. So I'm just going to say, we're actually going to cheat a little bit here because, because we're not actually going to bother writing anything to disk. Not really any use in writing things to disk for a demo. And so instead we're going to use this simple mini channel monitor object that exists to do most of the underlying channel monitoring, normally you would take this object and wrap it around your own thing to write things to disk, and then you would use it as the underlying object which actually monitors the chain and generates transactions and multiplexes events. But we're going to cheat a little bit because why do we care about being safe? We're on reg test and it's just a demo. So let me...
Why did you bother with the estimator if it's just a demo?
You do have to have fees on reg test. I suppose I could have written a fee estimator that always returns 1 Satoshi per byte or something, but still need something, right? Channel monitor. New channel monitor. So you have to give it an underlying chain interface that allows it to register. You look at this chain interface. Allows you to register a list of things to watch for, right? Because ultimately you might be running this on an SPV client. You might not necessarily be downloading the full chain, so you don't pass in every transaction. Instead, there's this interface that tells you, please watch for anything which spends this output, or please watch for this particular transaction. The watch all transactions method is actually only ever theoretically going to be implemented if you're running a watchtower and you don't have all the data available. But for most use cases, you only ever see events like this, where you'll notice here there's several different pieces that it tells you so that you can watch in several different ways, right? So for example, the neutrino filtering, in the current model, you actually don't have access to the out point, so you can't filter based on the out point, but you can filter based on the output script. And so, all of that data is given to you. So we're actually going to steal some of this stuff from, this is the current implementation that exists as a demoware. So let me just, now this is the one that does, this actually stores things to disk, but we don't need that. I am, however, going to copy a little bit of creating a key because, we have to create randomness in our keys, and I'm much too lazy to implement that. So this is, not going to bother with that. So we will just take a seed, read it from local random. I'm not going to bother rating it because screw rating things. And then we can actually, so we have Rest Lightning has a concept of a keys manager, which stores at least some level of the keys that you need for Lightning and can derive them deterministically, or of course you can provide your own keys if you want to do it that way, if you have your own key derivation function somehow. But the keys manager is just a little interface. Keys interface. So you'll notice that a lot of this stuff is pluggable interfaces. So like keys interface is a generic pluggable interface. You can provide the keys however you like, or of course you can use pre-created objects where you just simply initialize it with, so in this case we initialize it with, oops, that's channel keys, wrong one, keys manager. Initialize it with a seed and it derives everything else for you. There's not really any reason to need to implement everything yourself, unless of course you want to. I'm also going to steal the logging interface from my old implementation because why would I bother rewriting the logger? Of course, like any generic library, we have an interface for logging. In this case, I just ignore some of the routing table messages because otherwise, the second you turn a node on, you get or the second you connect to a peer, you get flooded with messages saying, "Hey, I've received a new update for a channel update because I'm currently syncing a routing table." Duh. You don't necessarily need to be flooded with that. So we're going to create a new.
Why you would need to match by the string?
Sorry.
Why would you need to match by the string? Right, received message. Is there possible to add some text types?
Oh, right. So you can match by the type. So in record, I can pull up the docs for this, but where's it? Logger. So record has some additional information. So for example, it has this level object, which can be error, warning, info, all of your standard things. So for a normal implementation, you probably would only ever log some subset of things, and I believe these particular messages are debug messages. And so just for the purpose of this demo, I'm including all debug messages except for messages where you receive these specific things. So there's some ability to match on kind of classes, but there's not necessarily ability to match on like exact error or exact messages at every level, right?
But you could have the message type there in the log record just and match by the number, right?
Right. You could have like a giant enum.
Repeat it for the live stream.
Right. So the question was whether or not you have to necessarily match by the string here. Of course, the API could have been implemented with some giant enum for every possible message type, and then you could match based on that enum. Instead, it's a little bit more flexible, and it gives you a little bit of information about the class of whether it's an error or whether it's just a generic debug message, and then some things about where it was generated. So you can actually see where in the code a given line was generated. Right, okay, so now we've created our keys. We've just done it based on a RNG. And now we're gonna get back to doing some more useful things. So because I'm gonna be lazy, I'm just gonna copy some things. Let's see, that's private keys. This is all stuff for actually bothering to make sure you have, yeah, so here's our channel manager. Network, estimator, monitor, chain monitor. Yeah, right. Okay. Where's our monitor? Chain monitor. Here we go. Right. Right. So our chain monitor is this simple thing that, again, is just this little object that I'd previously implemented, cheated a little bit. Is just this thing that pulls the RPC in Bitcoin Core to download the current transaction, or the current blockchain, pulls it every few seconds to ensure that it has the latest version, or latest chain. So where's the creation of that chain interface? Yeah, here we go. Oh, right, yeah. Yeah. Right. Let's skip that. So back to our monitor. I'm going to create one of these things, give it the chain monitor. There's a number of things where it's kind of separated, right? So there's a separate interface for I'd like to broadcast a transaction versus I'd like to get the current chain, but there's not really any reason to, often you would be able to implement these on the same object. So again, there's a lot of flexibility in this API, but at the same time with, an extra 30 characters of writing glue code, it doesn't really make much of a difference for you. You can just kind of ignore all of the flexibility just by writing a tiny bit more glue. So what are our arguments for channel manager? Create one, fee estimator, monitor. So this is the chain monitor. The chain monitor also implements the transaction broadcasting interface, our logger, our keys manager, which is this keys thing, and this config object, which we're just gonna create a new generic version. I'm also gonna put this in an arc. Right, so let's see if that actually builds. Likely not, but keys manager. Oh, need to include all of these things. I really should have just included everything before the demo. But I suppose I think that's the right path. Keys manager. What's the path for keys manager? This. Chain network. Oop. Uh-oh. What did we do? St8. So expected 8 parameters gave 7. Oops. Network, estimator, and monitor. Right. All right, well, I'm going to not do all of this, but it almost works. So it almost compiled. Instead of boring you all to death, I will just switch to this a little bit. But so you can see the general structure here is actually the same. Actually, the one on the right is the sample demo that was written about 6 months ago. But it does a bunch more work, but almost all of the additional work that it does is things like right here, right, once we've created some of the keys, we import those keys into the Bitcoin Core wallet so that when the internal Lightning node generates transactions which are relevant for your on-chain wallet, the Bitcoin Core wallet will just pick them up and start using them. We don't actually have to do any of the work in Rust Lightning. And it also actually implements things like writing things to disk. There's neat, relatively simple interface, right? So this is just deserializing the entirety of our channel state. You just read it directly from the file, and then it actually gives you, as a return value, both the channel manager, right? So this object that manages all of your local state, and also the current best block hash that it saw. And so then from there, you just replay the chain from that block hash to the current chain state, whatever that is. Theoretically, of course, if you're running a wallet that has this all integrated top to bottom, then hopefully that chain hash is the last tip that your wallet saw. Otherwise, something got a little confused. But either way, you just replay the chain from where it was. So now we get into a little bit more meat, right? So we have this router object. Again, it's just a ton of glue here where you get your node secret, you give that to the router, you connect it to the logger, you connect it to all these things together, and then, of course, we're also going to create this peer manager, which is just the thing that manages all your connections, create a list of the payment preimages, which you'll need eventually. I believe this sample implementation doesn't even bother to write payment preimages to disk because, your node never crashes, right? And then bind to the port, and then that's it. Like, by the time you've gotten here, which is really, what, maybe 100 lines? Not even, 100 lines of glue. You've read in all of the on-chain state. I guess it doesn't tell you. But by the time you've written about 100 lines of glue code, yeah, just over 100 lines of code. You've read in the chain state, you've initialized everything, and you're running a full Lightning node. Then you have to actually do things. And so this sample app here actually provides a full shell interface. And so we'll actually pull that up here. RPC. Make sure this is actually built. Oh, look, it doesn't compile. 157. Then, as soon as it finishes building, slash target debug lightning Bitcoin RPC user host. What did you say the port was for a rig test?
2883332.
Really? Okay. All right, let me kill this Bitcoin node. RPC user, RPC password. All right, 28332 and oops. No, that's not right.
I think
Felix, you lied to me.
18443.
18443. Well, now it's definitely 18443. 8443. Oh, whoops. Right, I didn't pass that correctly. And it actually takes a path for node 1 data, the data. Right, so it's now, created a node, it generated a key, started, it bound to a port, it's ready to accept incoming connections. Of course, it can't do very much there. Come on, die. Really? Okay, let me run this so that we can run a second one of these, and we'll connect them to each other. Bitcoin Rust, Lightning, Bitcoin RPC. 8. 2 data. Right, so now we've created 2 nodes, and let's, in theory, they should be able to connect to each other. And yeah, look at that. Got new inbound connection. And of course, so this is actually the log output from Rust Lightning. You can format it however you like, but the formatter actually prints the full path to the, you get the line number and everything, but of course you could just take the string from the interface, so that's kind of up to you. So we can list peers, and you can see that we're connected. So let's see, if we create a new channel, what's our pub key? New value. I assume that's in Satoshis, I don't actually know. Right, so we tried to create a channel, and then we called fund raw transaction, which is the Bitcoin RPC interface to get a transaction, and of course we don't have any funds. So let me first mine some blocks. Bin, client, RPC user, RPC password, pass. What's our RPC port equals 18443. Rig test and generate 10. New address. Does anyone know how to use these fucking things? Oh, is it? N blocks, 10 address. There you go. Let's generate 200 blocks, because, all right. Now this thing, I mean, you can see it dumping all these messages, connected blocks. Obviously got new blocks. Oops. It's sad. Whatever, doesn't matter. So now if we try this again and we create a channel, of course, I'm also tailing the Bitcoin Core debug logs, which makes it hard to read things. But where's my command? There it is. Create a channel. Oh, no, that's connect. Where did I? Oh, did I create it over here? No. All right, whatever. Let's see. I killed the thing. All right, so let's try this again. node ID, connect node ID at localhost, new channel, node ID, 1,000 satoshis, and look, we've created the channel. In fact, we've even added the transaction to our wallet. You can see this is from the Bitcoin Core log, so you can see add to wallet, right? Because we've broadcast this transaction that spent, we called fund raw transaction on the Bitcoin Core APC interface, so it added its own funds from its own wallet, and then once we broadcast that transaction, of course, Bitcoin Core identified that as its own transaction because it lost money from that transaction. So let's mine some blocks. Well, let's mine one block, and we can see one transaction matched our filter, right? So that is the chain monitoring interface that I described earlier. When it provides information about which transactions to watch for, it scanned the block and it saw that one of the transactions matched something that it had been told to watch for, and so of course you can see it there. And if we list channels, we've got this channel. It even has a short ID. Of course, short ID is calculated from the position in the block, and so obviously it has to have identified a block. So let's confirm this channel. New best block. I don't actually know how many. Here we go. Yeah. So you can see once we added 3 blocks, it generated all of these messages. So type 259, which I believe is funding locked. So it actually exchanged the messages and said, hi, I have the channel's been confirmed on both sides. So theoretically, the channel's been confirmed and we can get an invoice. Of course, I don't actually remember any of the commands, but P. Right, so it sends an invoice and we can send 1,000 satoshis. Oop, wrong network in invoice. Oh, great. It's on testnet and not reg test. Well, it does work, I promise. On testnet. Testnet, right. This is the problem. Just match or false. Oops, and false. So let's just fix that because we don't actually need safety checks, do we? And so if we run these, connect them again. One connected, and we can see all of the fun messages that get exchanged. And again, if we create an invoice and send, it generated all these messages, it sent. We sent a revoke and ACK message, and actually the current code has a delay of 60 seconds before it actually handles the result, just because I was testing things and wanted to test things, but in 60 seconds, hopefully you will see more messages get exchanged after it provides the pre-image to Rust Lightning, right? So it's actually, I'll show that while we're waiting. So Rust Lightning has a general kind of events interface, right? So every time you kind of do anything with the library, it might generate an event that you need to handle. And so we can go up to where that's handled up here. So the event handler just polls occasionally for whether or not there's an event, and then it matches what the type of event is. So we obviously already went through funding generation ready. And this is the logic that called create raw transaction and fund raw transaction, which is the thing that fails initially, of course, and actually creates the transaction for Bitcoin Core and then sends it. But of course, down here we have this payment received, which is where we saw this nice print from, right? This handling payment received in 60 seconds. Right, Rust Lightning, because Rust Lightning doesn't do its own data storage, it expects you to do data storage for things, for example, like storing the payment pre-images for invoices that you might have generated. And so you get these nice events that's like, hey, I've received a payment. Just give me the payment preimage that matches this payment hash, and then you will get this wonderful amount. And then, of course, we look it up, and we say, hey, channel manager, yes, I do have the payment preimage. Here you go. And that's it. It kind of handles the rest of it. And so, of course, we can see where that happened. Money, money. We got 1,000 Satoshis because we provided the payment preimage to the channel manager, and the channel manager said, yep, you're good. I've got money for you. And then, of course, at that point, the channel manager generates all of the relevant events for you. It generates all the messages. We generate update HTLCs, so we send updates to our peer. We say, hey, yes, I've got the preimage, and then it does all of the actual handshaking and all of the message exchanging with the peer for you, all under the hood, and all you had to do was provide it the payment preimage. Of course, if you don't have the payment preimage, you fail it backwards, and you say, I don't know that. And so, of course, it also has a payment sent money message, and we can see that from the other node here, less money. And it provides you the payment preimage that was provided to you by the person who received the funds. So that's your proof that you successfully sent the funds. Yeah, so from top to bottom, for the most part, we can see that we had, what, line 84? An entire Rust Lightning implementation that actually stores things to disk and sets everything up and reads it is about 390 lines of code, excluding glue for actually making Bitcoin Core RPC calls, and obviously also excluding a ton of command line parsing and argument parsing that ends up being about another 100 lines of code. So yeah, that's pretty much it. I figure you all have some interesting questions, but yeah, you can see it actually managed to create channels, and obviously it also creates channels with LND and C Lightning, and that's reasonably well tested. We actually only got it creating channels with itself yesterday, but LND and C Lightning were easy. But yeah, so that's Rust Lightning. It works pretty reliably. We have spent a ton of effort on testing, and there's some great test infrastructure, really cool fuzzing, protocol level fuzzing to beat the crap out of the protocol implementation to make sure that it is self-consistent and never loses funds. And we've been throwing years of CPU hours at it, and found a number of bugs, but luckily fixed them all. So yeah, it's a cool little implementation. I don't know how much time we have for Q&A, but we'll probably do a few before Fabrice wants to go up.
Is this self-sufficient, or do we have downside dependencies of some kind?
Sorry?
Is this self-sufficient, or do you have dependencies on the?
For the most part, there's no dependencies in Rust Lightning itself. It uses, so there's a whole community of Rust Bitcoin implementations written in Rust, so like all of the underlying data structures and whatnot are and hash function implementations and whatnot are from those libraries, which I also work on, and then it uses libsecp for signing and whatnot. But that's pretty much it when it comes to dependencies. This particular sample implementation has a bunch of dependencies for the network logic and the network stack, but you could use whatever you wanted there. So.
You said that the network stack is kind of independent to whatever it's working on, really bare metal or something. But how does it work? I mean, it surely uses fork or something else, threading or something like this.
No, so the Rust Lightning is designed, so the question was, how does, if the network stack's independent, surely there's some kind of threading under the hood or something like that. So Rust Lightning is designed, the end goal is that it makes no syscalls. with the exception of malloc. We're not going to get rid of malloc, but everything else should be completely optional. And so this enables you to run on an embedded device where you don't have threading or whatnot. But of course, also in this sample implementation using Tokyo, it has all kinds of threading. But the actual kind of interface that you have to implement, if I can pull it up here, is right, yeah, socket descriptor. So you provide this little interface object that kind of describes a socket from the point of view of the OS, and then Rust Lightning just calls that interface and says, hi, yes, I'd like to send, here's some arbitrary data, please send it to the peer, or just hang up on this peer. So it ends up, you can obviously write glue that converts this into standard select, write, and read syscalls in 20 lines of code. I happen to use this fancy Rust networking implementation, and I have a demo or a supported optional additional dependency that you can add that implements that all for you, but there's no inherent threading model that's required here. It does support threading, so it can take all the required locks and mutexes so that it's completely thread safe if you use it that way, but I'd like to make the mutex is completely optional in case you're on a operating system or you're on an embedded device where you don't have such syscalls available and you only have malloc. All right, Fabrice, looks like you're up.
Just one question. What are the things you like and dislike the most about Rust? I'm going to try to come back to this.
Yeah, Rust is still a little new. It's pretty stable. This is Firefox, and Firefox is like 30% written in Rust at this point. So it's not like it's a completely unstable, unusable language. A lot of the networking stack that's built into Rust is still kind of being actively developed, which is, of course, the nice part about Rust being a C-callable language. You can take Rust Lightning, you can call it from any language that can call C functions, right? So there's no kind of inherent language limitations. You don't have to write something in Rust to use Rust Lightning. Anything can call a C function, so you can theoretically build a Lightning node pretty trivially based on Rust Lightning in Python or whatever you want, right? Or on a mobile device, something like that. So for Rust, just building a C-callable interface is super great and pretty stable. It's pretty straightforward. Once you start getting into some of the more complicated things like async networking, the borrow checker gets in your way a little bit more, so that can be annoying. But in terms of, I've been super, super happy with it, specifically for this use case of blind C-callable interface that you can embed anywhere, because Rust is relatively low level, but also very safe in the sense that you have this borrow checker and you don't have you have the optional ability, but Rust Lightning obviously doesn't use it to scribble all over memory or have those kinds of overflows that you see in other C code and other things that are C-callable, of course.
Do you know if there's like a full Lightning node implementation being worked on based on Rust Lightning?
The question was if there's a full Lightning node implementation being worked on based on Rust Lightning. A supported one, not as far as I know. I've been working with some folks. I've been trying to work with, I don't think it makes a lot of sense to build yet another freestanding Lightning daemon based on Rust Lightning. LND, C Lightning, Eclair work great. It's more targeted at and more interesting for if you have an existing mobile wallet or you have an existing wallet to integrate Lightning using Rust Lightning, because in a few hundred lines of code you should be able to do that, and it's mostly just plugging in the glue between your existing chain data store and your existing wallet to Rust Lightning. I'm not aware of anyone who has started that project yet, but I've been talking to a number of wallet authors about that. I think a lot of the kind of more well-supported or like well-established Bitcoin wallets aren't quite at the point where they're ready to integrate Lightning as a full-fledged thing, just because there's a ton of UX hurdles right now. But as those get resolved, it probably makes a lot more sense. But by the time they're ready for it, Breast Lightning is going to be a nice, useful thing for them, I hope.
What would you say is like the main, what do you need to work on mainly before it's like a nice thing you want it to be?
The one thing left, I want the Lightning 1.1 spec, because right now Lightning, the fee agreement across peers is essentially disabled on every node, which is relatively unsafe because your peer can tell you whatever it wants for future fee rates, and then you're kind of screwed if the fee rates change materially. And that's especially worse when the user's providing the fee rates, right? So there's kind of this pseudo consensus around fee rates in Lightning, and as long as there's only a few node softwares and they have their own fee estimators built in, it's a little bit easier to have that kind of consensus. As soon as we start saying like, oh yeah, please BYO fee estimator, then you end up with a lot more risk for users not being able to get punishment transactions confirmed. So I'm kind of concerned about that on a broad scale in Lightning, and I don't necessarily want to ship something that makes it even worse until that's fixed. Of course, that's Lightning 1.1, right? That's fixable at a protocol level, so mostly I want that. But for the most part, I mean, you can see there's relatively verbose documentation. It maybe is too verbose, but there's relatively reasonable documentation there. It all is pretty stable. There's some things left to do on on-chain punishment, but the test coverage is great. Because it's an embeddable library, all of the tests are create free nodes, give them funds, hook them together, send messages between them, reorder the messages in weird ways, delay the delivery of the messages in weird ways, and make sure the node comes out correctly, which is a really difficult test to write for LND or C Lightning or something, where it's like a full freestanding daemon and trying to intercept the messages and deliver them out of order in some weird state that isn't really realistic, but a peer might do to you maliciously, is a really hard test to write for something like that. Whereas for us Lightning, that's all of our tests. And in fact, that's also fuzzer, right? We have a fuzz target which stands up nodes, connects them to each other, and then the fuzzer gets to decide what actions get taken and in what order messages get delivered, and tries to break the state machine, which again is just not something you could write for a freestanding daemon. But since it's an embeddable Lightning daemon or Lightning node that has no kind of external state that it's observing, it's really easy to write in fuzzer, and then you just throw it at AFL or libfuzzer or whatever. I don't want to step too much into Fabrice's time, but
Yeah,
if you want to, I mean, if Fabrice, you can hook up your laptop while I keep taking more questions.
Yeah, so my question was basically covered by the previous question, but still, I was meaning to ask, so would you say that Rust Lightning is now feature complete in the sense that it's compliant with Wallet 1.0?
Yeah, I think it has been for a while. It's not feature complete in the sense that all of the potential punishment angles are correctly handled, but it is, like, API-wise, I would call it very significantly feature complete. The API has been pretty stable. It's well documented. It's relatively, I think, relatively easy to write something against. At least if you're writing against Rust. I haven't actually written a C wrapper for it, but theoretically also should be relatively easy for that as well. But I would call the API pretty stable. The low-level implementation is mostly there. It's like 90% there, but not quite. And some of that's also waiting on Lightning spec changes, because I don't really want to write stuff that I know isn't realistically safe, and I don't want to bother writing stuff that I'm going to throw away in 3 weeks once the spec changes, or at this rate, 6 months once the spec changes. Felix?
So the three main Lightning implementations, they kind of like wrote the spec together.
Mm-hmm.
Kind of like, I mean, there was the written word, and then like the one, the stuff that they like new from the meetings.
Right.
You wrote this, you implemented being like independent, kind of like just from the spec. Was the spec complete enough?
There were definitely some parts in the spec that weren't clear, that have been resolved to some extent. I think, admittedly, I didn't do as good a job resolving the ambiguities in the spec as some of the other folks, like the Japanese company, what's it called? Ptarmigan. They've probably contributed more towards resolving ambiguities. The spec requires a lot of it doesn't provide you the high-level understanding of how Lightning works in a theory sense, which you kind of need to understand a lot of the, a lot of the spec can be read as ambiguous unless you know the theory and you think about it and you're like, okay, if it worked in this weird way, in this potential reading way, it wouldn't be secure, so it must work in this other way. And so you kind of need that intuition already in order to make sense of some of it. But if you have that, it's readable. There's definitely some parts that are still ambiguous, but for the most part, it's readable. You can tell which ones were written by who, because some of the bolts have no context and lots of specifications. Rusty. Some of the bolts have a lot of context and are really light on actual detailed how it works. So, yeah, but for the most part, it wasn't too terrible.